13.8 billion years ago, everything we know burst into existence from a point smaller than an atom. Yet the James Webb Space Telescope has uncovered galaxies that were already ancient, while the universe itself should have still been an infant. We're witnessing stars that forged heavy elements long before the cosmos should have had the time to create them. Massive black holes that grew at impossible speeds, and structures so perfectly organized they have no place in a chaotic young universe. The most powerful telescope ever built wasn't designed to dismantle our origin story, but that is exactly what it's beginning to do. Prepare yourselves. We begin. James Webb Telescope. The James Webb Space Telescope cost $10 billion and required 30 years to build, but it wasn't created for prettier space photos. Scientists launched it with a mission: confirm that our cosmic creation story was correct. For decades, we've lived by a simple narrative. The Big Bang occurred 13.8 billion years ago, followed by 400 million years of cosmic darkness. During that time, the first stars formed slowly, composed only of hydrogen and helium. Galaxies were supposed to grow gradually, chaotically, through billions of years of collisions and mergers. This wasn't just a theory, it was the backbone of modern cosmology. Every textbook, every documentary, every explanation of our cosmic origins depended on it. James Webb was engineered to be the ultimate witness. Its infrared eyes could peer into the cosmic dawn and reveal the universe's primitive first stars struggling to ignite in the darkness. We expected to see a violent, disordered cosmos slowly assembling itself into the structure we know today. The telescope's mirrors were polished with perfect precision, its instruments tuned to catch the faintest whispers of ancient light. Scientists were ready to celebrate as the telescope confirmed what simulations had predicted for decades. The early universe, we believed, should look young, messy, and wildly unorganized. But when James Webb opened its golden eye and looked back toward the beginning of time, it didn't confirm anything. Instead, it revealed something that shook astronomers to their core. The instrument designed to validate our origin story might instead be dismantling it. What we discovered challenges not just how galaxies formed, but the entire timeline of cosmic evolution, and the implications extend far beyond astronomy. If the fundamental story we tell about reality is wrong, what does that mean for physics, philosophy, and our place in the cosmos? The data hidden within James Webb's observations might force us to rewrite the first chapter of existence itself. But this was only the beginning of what stared back at us from the cosmic dawn. 400 million years after the Big Bang, the universe should have been a barren wasteland. Imagine compressing the entire cosmic timeline into a single year. At this stage, we'd still be on January 2nd. Galaxies should have been tiny, primitive clusters of the very first stars.
Yet James Webb found vast, mature galaxies, structures that looked like they had existed for billions of years. These weren't fragile clouds of newborn stars. These were colossal systems with masses equivalent to 100 billion suns, complete with spiral arms and central bulges. For comparison, the Milky Way took more than 13 billion years to reach that level of organization. And somehow, these galaxies did it when the universe was barely out of infancy. The numbers make no sense. Simulations showed that such massive galaxies should require at least 2 billion years to form through gradual mergers, but we see them when the universe was only 400 million years old. It's like finding a fully grown oak tree in a garden planted yesterday. Dr. Ivo Lab from Swinburne University described these discoveries as galaxy monsters that shouldn't exist. His team found galaxies so massive they contain nearly as much matter as all the stars expected in the entire observable universe at that time. The math collapses under our current understanding of cosmic evolution. And even stranger is how organized these galaxies appear. The Big Bang model predicts early galaxies should be chaotic, irregular, and slowly evolving. But James Webb is showing spiral structures, central black holes, and coordinated star-forming regions, features that typically require billions of years to develop. This forces astronomers to consider an uncomfortable possibility. Either galaxies form far faster than we ever imagined, or our cosmic timeline is fundamentally wrong. Some scientists have begun whispering alternative theories, ideas that, if true, would overturn decades of belief about the universe. And the consequences stretch far beyond galaxy formation. Massive galaxies appearing this early should have reshaped the evolution of the entire universe. Their gravitational influence should have left signatures we don't see elsewhere. Yet the evidence continues to grow. These impossible galaxies are real. In the beginning, the universe held only 3 elements: hydrogen, helium, and faint traces of lithium. Everything else on the periodic table required stars to forge them in their cores and scatter them through space in explosive deaths. This process should take billions of years. Yet James Webb is discovering heavy elements in galaxies that formed when the cosmos was still in its infancy.
Picture a star as a kind of cosmic kitchen. It begins with the simplest ingredients, hydrogen and helium, and slowly transforms them into heavier elements through nuclear fusion: carbon, oxygen, silicon, iron. But these ingredients don't appear all at once. They require entire generations of stars to live, die, and be reborn. Those first stars had to burn through their brief, violent lives, explode as supernovas, and enrich the universe with heavy elements before the next generation could form planets in complex chemistry. This process is a slow cosmic assembly line that cannot be rushed. The most massive stars may burn bright and die young, but even the fastest stellar cycle takes hundreds of millions of years to produce meaningful amounts of heavy elements. Yet, when the universe was only 400 million years old, barely an infant, James Webb detected clear signatures of oxygen, carbon, silicon, even magnesium. And these weren't faint traces that could be hand-waved away by unusual stellar behavior. We're seeing levels of metal enrichment that imply multiple cycles of star birth and death. Dr. Emma Curtis Leake, who led some of the key observations, described these early galaxies as having metallicities comparable to much later cosmic eras. The spectra are unmistakable. These ancient galaxies contain elements that simply should not exist yet, forcing us to question the foundations of cosmic chemistry. And that mystery is mild compared to what came next. Imagine trying to construct a skyscraper in the middle of an earthquake while blindfolded. That is what early galaxy formation should have looked like: a turbulent, violent universe filled with crashing gas clouds and colliding dark matter halos. Galaxies, according to our models, should have grown slowly through chaotic mergers spanning billions of years. Instead, James Webb revealed galaxies that looked as if they had been designed by a cosmic architect. The Hubble Space Telescope had already shown that distant galaxies grow more irregular the farther back in time we look, a comforting confirmation that early galaxies were messy, unrefined structures. So Webb was expected to show us even earlier, even clumsier formations, cosmic toddlers stumbling in the dark. But what it found were galaxies with defined spiral arms, orderly central bulges, and coherent star-forming regions, features that demand stability, balance, and billions of years of evolution. In our local universe, only the most mature galaxies display this level of organization. Yet here they were, at the dawn of cosmic time, looking impossibly complete. Dr. Stephen Finkelstein from the University of Texas described it as discovering fully grown adults in a cosmic nursery. This level of structure contradicts everything we know about hierarchical evolution, which expects small objects to merge into larger ones over vast stretches of time. These galaxies seem to have skipped their chaotic childhood entirely. The disk structures Webb observed deepen the puzzle. Today, galaxy disks form gradually as gas settles into orderly rotation over hundreds of millions of years. Frequent mergers in the early universe should have shredded any delicate disks that tried to form. Yet, Webb shows pristine spiral patterns that look untouched. Even stranger are the supermassive black holes at their centers, perfectly balanced with their host galaxies.
In the modern universe, this relationship emerges over billions of years through an intricate feedback dance between star formation and black hole growth. Finding such coordination so early suggests mechanisms we don't yet understand. The implications are profound. If galaxies can assemble themselves this quickly, then our entire understanding of cosmic structure formation may need to be rewritten. The galaxies Webb found should not appear for billions of years. And their precision only leads to an even more disturbing discovery: rotation speeds that break the rules of physics. Galaxies spin like cosmic hurricanes held together by the invisible grip of dark matter halos. The faster they rotate, the more mass they need to avoid flying apart. This relationship between rotation speed and mass is one of astronomy's most trusted laws. Yet Webb found early galaxies spinning so rapidly they should have torn themselves apart. When astronomers measure the velocity of stars in a galaxy's disk, they can calculate its total mass. It's like watching cars race around a circular track. The faster they move without flying off, the steeper the banking must be. In galaxies, that banking is gravity, mostly dark matter. But these early galaxies rotate at speeds requiring dark matter halos far larger than anything predicted by simulations. Some spin at 300 kilometers per second when physics says they should max out around 150 kilometers per second.
It's like watching a motorcycle take a hairpin turn at double the speed that should send it crashing into the wall. Dr. Claude-André Faucher-Giguère from Northwestern University, who studies rotation curves, describes these galaxies as outright impossible under current models. The halos needed to stabilize such rotation would be so massive they should dominate their cosmic neighborhoods. Yet we find no evidence of such monstrous halos. Even more baffling is how quickly these galaxies reached such extreme spin speeds. In our universe today, disks gain their spin gradually as gas settles into stable orbits over immense timescales. But these ancient galaxies seem to have reached full spin almost immediately, like a figure skater stepping onto the ice already in a perfect pirouette. Angular momentum conservation only deepens the paradox. As galaxies collapse from gas clouds, they should spin up slowly, pulling in their arms like a skater drawing in their limbs. But Webb's measurements suggest these galaxies began with far more angular momentum than the cosmic web should have supplied. Some theorists now explore exotic ideas: modified gravity, alternative dark matter, entirely new physics. Others propose mechanisms that we've never even considered. Yet every explanation requires abandoning well-tested principles or accepting that the early universe played by completely different rules. And these spinning paradoxes lead to another impossibility: collisions happening before galaxies should even exist. Galaxy mergers are slow, dramatic events unfolding over hundreds of millions of years. When two galaxies collide, their gravitational choreography produces tidal tails, stellar streams, and unmistakable distortions, cosmic forensic evidence. Webb found these signatures in galaxies so young that collisions shouldn't have been possible at all. The timeline issue is severe. According to our models, the earliest galaxies were tiny, isolated star clusters separated by enormous distances, cosmic hermits too far apart to interact. Major mergers shouldn't occur until at least a billion years after the Big Bang, when galaxies were large and close enough to influence each other. Yet Webb reveals tidal streams, double nuclei, and warped structures only produced by gravitational encounters just 400 million years after the universe began. Dr. John Silverman from the Kavli Institute described it as finding car crashes in a world where cars haven't been invented yet. Nearly every early galaxy Webb observed bears signs of a collision. It's as if the young universe experienced a cosmic traffic jam. And even more troubling, these weren't small galaxies merging with tiny neighbors. These are major mergers between massive, well-developed systems. We're not looking at small galaxies swallowing tiny neighbors. These are major collisions between systems that were already enormous and fully developed. The energy needed to tear apart such massive galaxies
and then reorganize them into the clean structures we observe should take billions of years. And yet James Webb is showing us the aftermath of these collisions when the universe was barely 500 million years old. The implications ripple through every part of cosmic evolution. If gigantic mergers were happening this early, they would have ignited explosive waves of star formation and fueled central black holes at rates far beyond anything predicted. Such extreme activity should have left unmistakable fingerprints throughout the universe, signatures that we simply do not see in any other record of cosmic history. This has led some astronomers to wonder if our entire timeline of structure formation is flawed. Maybe the universe assembled itself far more quickly than we ever believed possible.
But the problem of impossible timing doesn't end with galaxy mergers. What Webb uncovered next was even more unsettling. It challenges the accuracy of the universe's very first photograph, the baby picture that doesn't match the child. The cosmic microwave background is often described as the universe's newborn portrait, a faint glow preserved from just 380,000 years after the Big Bang. Encoded in this ancient light are tiny density variations, seeds that should eventually grow into galaxies, stars, and everything we see today. But James Webb's discoveries suggest this baby picture may be lying to us. According to the cosmic microwave background, the early universe was astonishingly smooth. Tiny ripples, just 1 part in 100,000, should have grown very slowly over billions of years into today's structures. Cosmologists have simulated this evolution with extreme precision. These models tell us that at the epoch Webb is observing, galaxies should be small, irregular, and rare. But that's not what Webb sees. The enormous orderly galaxies revealed by James Webb require initial density fluctuations far larger than anything recorded in the cosmic microwave background. It's like discovering full-grown trees in a field where the soil test says only grass seeds were planted. Dr. Rajesh Minali of the University of California, comparing Webb's findings with CMB predictions, describes the mismatch as fundamentally troubling. The early universe appears to have possessed far greater structure-forming power than the cosmic baby picture allows. And the discrepancy isn't minor. Some galaxies are so massive they would require regions of space far denser than the CMB says should exist. The odds of such galaxies forming from the recorded initial conditions are effectively zero. This creates a cosmological paradox at the deepest level. Either our interpretation of the cosmic microwave background is flawed, or our theory of how structure grows from those initial seeds needs to be rewritten entirely. Both possibilities require abandoning major assumptions about cosmic evolution. Some theorists now explore exotic solutions, primordial black holes, altered gravity, or radically different early universe scenarios. Others suggest the cosmic microwave background may not be the pristine record of initial conditions we believed it to be. But the contradictions only intensify. Black holes that grow too fast to be real. Quasars are the universe's most powerful beacons, brilliant lighthouses fueled by supermassive black holes that devour matter at incredible speeds, unleashing energy across billions of light years. These black holes weigh millions to billions of solar masses. Yet, James Webb has discovered fully mature quasars, shining at a time when black holes should barely have formed at all. Building a supermassive black hole is like constructing a skyscraper 1 grain of sand at a time. The growth of a black hole demands patience and an enormous supply of material. Even under the best possible circumstances, a black hole can only feed so quickly. The energy released as it devours matter heats surrounding gas and blasts it outward, slowing the black hole's own growth. This natural speed limit means that even the most voracious black holes need billions of years to reach supermassive scales. The physics is unforgiving. As matter spirals inward, it heats up, glows brilliantly, and unleashes intense radiation before vanishing forever. This radiation acts like a cosmic regulator, restricting how much matter can fall in at any moment. This limit, known as the Eddington limit, implies that a black hole starting at 1,000 solar masses would require over 1 billion years to grow into a 1 billion solar mass giant.
Yet James Webb has revealed quasars powered by billion solar mass black holes when the universe was only 600 million years old. These are not small black holes on their way to maturity. They are already fully grown titans, reshaping their galaxies and blazing as some of the brightest objects in existence. Dr. Xiaohui Fan of the University of Arizona compares these early quasars to finding adult elephants in a nursery filled with mice. The growth rates needed to produce such massive black holes exceed theoretical limits by a factor of 10 or more. Either our understanding of black hole physics is missing something fundamental, or these black holes began life far larger than our models allow. The mystery deepens when considering their origins. The very first black holes should have formed from the collapse of the universe's earliest stars, stars that themselves required tens of millions of years to form and die. Those first seed black holes should have been only around 100 solar masses. Growing from 100 to 1 billion solar masses in just 600 million years, while obeying the Eddington limit, is mathematically impossible. It's like trying to drive from New York to Los Angeles in 1 hour while obeying the speed limit. Some theorists propose that the first black holes formed through entirely different mechanisms, perhaps collapsing directly from massive gas clouds and starting with far larger masses. Others suggest that black hole growth in the early universe did not obey the same physical limits we observe today. But these impossibly massive black holes are only part of the story. They are fueling something else: explosive star formation. Stars form inside vast molecular clouds where gravity slowly compresses gas and dust until nuclear fusion flickers to life. This process has natural limits governed by the physics of matter under extreme conditions. Yet James Webb has found galaxies forming stars at rates so extreme that they violate every theoretical ceiling we've established for stellar birth. In the modern universe, even the most intense star-forming galaxies convert only about 1% of their gas into stars every million years. This inefficiency exists because star formation is messy. Massive stars blow fierce winds and explode as supernovas, heating and scattering nearby gas. This feedback acts like a thermostat, preventing runaway star birth. Even today's most extreme star-forming galaxies manage around 1,000 new stars per year, a rate already considered extraordinary. But the early galaxies seen by James Webb are forming over 10,000 stars per year, and doing so for hundreds of millions of years. Dr. Pascal Ost of the University of Geneva describes this as finding cosmic factories running at 10 times their maximum rated capacity. Such intense star formation should heat and expel the remaining gas almost instantly, shutting the process down. Yet these galaxies maintain their furious pace. The physics simply doesn't add up. Creating 10,000 stars per year requires devouring gas at a rate that should drain even the largest reservoirs in a cosmic blink. These galaxies would need constant infusions of new material. But the early universe was far too sparse to provide such rapid resupply. Even stranger is that these galaxies managed to retain their gas despite the violent feedback. In today's universe, rapid star formation produces winds powerful enough to strip a galaxy bare. But these ancient galaxies appear immune, as if protected by physics we do not yet understand.
This suggests that star formation in the early universe may have followed rules radically different from those we see today. Perhaps the gas was denser, perhaps stellar feedback was weaker, or perhaps gravitational conditions operated differently in the cosmos's youth. Some astronomers even suggest primordial gas had unusual properties, long since vanished from the modern universe. Others argue that our understanding of stellar feedback and gas dynamics requires a fundamental overhaul. But the impossibility doesn't stop there. A universe that organized itself too quickly. The early universe should have been pure chaos, a violent, turbulent environment where matter crashed together randomly as gravity attempted to impose order. Large-scale cosmic structure should have slowly emerged over billions of years. Instead, James Webb has revealed a level of organization that suggests the universe began assembling itself with remarkable speed, as if it already knew the blueprint. Imagine the cosmic web as a three-dimensional spider web stretching across billions of light years, with galaxies hanging like dewdrops along invisible filaments of dark matter. This vast structure is one of the most elegant features of the modern universe. Simulations show that such organized patterns should require at least 1 billion years to emerge from the smooth initial conditions after the Big Bang. But Webb has uncovered signs of large-scale structure when the universe was only a few 100 million years old. We are seeing aligned galaxy clusters, coordinated star formation patterns across massive distances, and gravitational influences between objects that should have been isolated islands in space. Dr. Casey Popovich of Texas A&M describes these findings as discovering a completed jigsaw puzzle where we expected to find scattered pieces. The gravitational coordination between distant systems demands a cosmic web that developed far faster than our models permit, and this organization appears at multiple scales simultaneously. Individual galaxies are more structured than expected. Groups and clusters have formed too early, and the gravitational binding energy needed to hold these systems together suggests assembly far beyond hierarchical evolution's predicted pace. Even more baffling is how these structures maintain coherence over vast distances. In the early universe, light simply hadn't had enough time to travel between many of these regions, meaning they couldn't coordinate their behavior through any known physical process. Yet the data shows coordination across distances that should be causally disconnected. This strikes at the heart of our understanding of how the universe evolved, from near uniformity to the structured cosmos we see today. If large-scale structure formed this quickly, then the initial conditions after the Big Bang must have been very different from what inflation theory predicts. Some cosmologists turn to ideas involving cosmic phase transitions, primordial magnetic fields, or exotic forms of dark energy that could accelerate structure formation. Others question whether the early universe was ever as smooth and random as we assumed. But the shock doesn't stop there. Planets that shouldn't exist yet. Rocky planets like Earth require a cosmic recipe that is slow to prepare. Multiple generations of stars must forge heavy elements, supernovas must scatter them through space, and gravity must carefully assemble dust into pebbles, pebbles into rocks, and planets over at least 1 billion years. Yet James Webb has found hints of planetary systems in galaxies so young that the ingredients for rocky planets shouldn't even exist. Spectroscopic fingerprints reveal dust, maybe even early planetary debris, in galaxies less than 800 million years old. Dr. Kevin Heng of the University of Bern describes this as finding evidence of planet building during an era when the universe shouldn't even possess the materials to build planets. This pushes the timeline for potential life dramatically backwards. If rocky planets formed this early, the universe may have been filled with habitable worlds billions of years before our solar system existed. Even more intriguing are hints of atmospheric absorption, early signs of planets with chemical complexity, perhaps even primitive atmospheres. This suggests planetary systems may assemble far more quickly than our models allow, acting as miniature chemical laboratories only a few 100 million years after the Big Bang.
Perhaps dust grains clumped more efficiently in the early universe. Perhaps gravity worked differently in a denser cosmic environment. Or perhaps early planet formation followed mechanisms unknown in the modern universe. Whatever the case, these early planetary systems directly challenge the foundation of inflation theory. The telescope didn't uncover a single anomaly. It revealed an entire constellation of impossibilities. Massive galaxies where only tiny ones should exist. Heavy elements that formed far too early. Structures that should be chaotic yet appear perfectly organized. galaxies spinning faster than physics allows, collision signatures that predate any chance of interaction, star birth rates that shatter theoretical limits, and planetary systems assembled long before the universe had the ingredients to build them. Any one of these discoveries might have been dismissed as a strange outlier, but together they form a unified message. The universe is not following the script we wrote for it. Independent research teams using entirely different methods keep confirming the same story. Dr. Evo's measurements of galaxy masses have been verified repeatedly by groups using alternative techniques. Multiple surveys have independently detected early heavy elements. The impossible rotation speeds show up in velocity curves and in gravitational lensing data. And the most striking part? Every anomaly points in the same direction, toward a universe that assembled itself far faster, far earlier, and far more efficiently than the Big Bang model predicts. These aren't scattered inconsistencies that can be patched with small theoretical tweaks. They form a coherent pattern, a pattern suggesting our entire cosmic timeline is wrong. The statistical weight is now crushing. When astronomers calculate the odds that all these findings are merely measurement errors or rare flukes, the probability drops to nearly zero. We're not seeing coincidences. We're seeing systematic contradictions that demand explanation. This convergence of evidence is pushing physicists away from minor fixes and toward revolutionary alternatives. Dr. Sykes-Steen Subir-Sarkar of Oxford University calls it a paradigm crisis, a point where accumulated anomalies can no longer be absorbed by the existing theory. Science has been here before. Multiple independent clues once converged to overthrow the idea that Earth was the center of the universe. Multiple lines of evidence once forced acceptance of cosmic expansion. The cosmic microwave background once sealed the case for the Big Bang. Now, James Webb's discoveries may be converging toward the Big Bang's replacement. Scientific institutions are beginning to acknowledge that these discrepancies are not trivial. Major agencies are now funding research into alternative cosmologies, frameworks that could explain Webb's results without violating the laws of physics. Behind closed doors, physicists around the world are racing to build entirely new models of cosmic evolution. These aren't minor add-ons to the existing theory. They are deep reimaginings of the universe's history, models that could replace the Big Bang entirely. The urgency is real. The evidence is piling up faster than explanations can be constructed.
Dr. Neil Turok of the Perimeter Institute is developing cyclic cosmology, where the universe expands, collapses, and is reborn endlessly, each cycle preserving structural information that could explain the shockingly rapid organization seen by Webb. Dr. João Magoajo of Imperial College London is exploring variable speed of light cosmologies, where the speed of light itself was higher in the early universe, allowing distant regions to coordinate their evolution. Modified gravity theorists like Dr. Sabine Hossenfelder are investigating whether gravity behaved differently on cosmic scales or under extreme early universe conditions. Others are exploring multiverse physics, suggesting our universe may just be one pocket in a larger cosmic structure, with matter and information flowing between regions through unknown channels. Dr. Paul Frampton's bouncing universe models propose alternating phases of expansion and contraction, creating windows for extreme structure formation that match Webb's observations. Across the field, the traditional picture of a single Big Bang is being replaced by visions of multiple epochs, multiple universes, or multiple cycles, each with different physical laws. And with each new batch of James Webb data, more traditional explanations fall away. The crisis is no longer isolated to cosmology. Particle physics, gravitational theory, stellar evolution, all are being reconsidered simultaneously. Some of the most intriguing ideas involve emergent gravity, where gravity is not fundamental, but arises from deeper quantum processes. If gravity emerged differently in the early universe, cosmic structures could have formed with astonishing speed. But these new frameworks are pushing us toward a deeper shift, a challenge to our very understanding of space and time. Einstein's relativity taught us that space and time form a single dynamic fabric, shaped by matter and energy. This framework has been validated countless times. It is the foundation of modern cosmology. But James Webb is now revealing galaxies and structures that behave as if space-time itself did not yet operate under the rules we understand. Galaxies seem to form and coordinate in regions that should have been causally disconnected, regions where light had not had time to travel, making gravitational communication impossible. This suggests one of two things. Either space-time behaved differently in the early universe, or our understanding of its structure is incomplete. Dr. Lee Smolin of the Perimeter Institute is exploring theories where time itself is emergent, not fundamental. Under extreme early universe conditions, time may have flown differently or not at all. Other theorists suggest additional spatial dimensions may have been accessible in the universe's youth, allowing information to move faster than light in our familiar three-dimensional space. Some propose that the speed of light itself wasn't constant throughout cosmic history. If light traveled faster in the early universe, it would allow far-separated regions to communicate and synchronize their evolution, naturally explaining the large-scale order Webb uncovered. Dr. Carlo Rovelli of the French National Center for Scientific Research imagines space-time as discrete, granular, and radically altered under extreme early universe conditions, precisely the environment of the early universe. If space-time behaved differently, then many of the impossibilities recorded by Webb become feasible. The James Webb discoveries are forcing physicists to reconsider something once thought unshakable: the very nature of space-time. It's no longer just a question of galaxies forming too quickly. It's that they formed in ways that appear to break causality itself. For structures to organize, information has to travel across space so gravity can coordinate their growth. Yet many of the early, perfectly arranged structures Webb revealed lie at distances where light simply couldn't have crossed in time. Under our current understanding of space-time, their existence should be impossible. Dr. Lee Smolin of the Perimeter Institute has been exploring a radical idea that time itself may not be fundamental. In this view, the flow of time that we experience could be an emergent phenomenon that collapses under extreme cosmic conditions. If time behaved differently in the early universe, processes that seem impossible today might once have been completely natural. Other theories push even further. Some physicists propose that the early universe may have had additional spatial dimensions, accessible in cosmic youth, but hidden as the universe evolved. If true, these extra dimensions could have provided pathways for information or energy to travel faster than light in our familiar three-dimensional space, solving the mystery of the early universe's impossible coordination. Another possibility is that the speed of light itself wasn't constant throughout cosmic history. If light traveled faster in the early universe, it would allow far-separated regions to communicate and synchronize their evolution, naturally explaining the large-scale order Webb uncovered. Dr. Carlo Rovelli of the French National Center for Scientific Research has developed loop quantum gravity models, suggesting space-time is not continuous, but made of discrete, granular units. Under extreme early universe conditions, this pixelated space-time could behave in completely unfamiliar ways, allowing cosmic structures to grow through mechanisms impossible in classical relativity. These implications go beyond cosmology. If our understanding of time and space is fundamentally flawed, then quantum mechanics, gravity, and even the possibility of time travel might need to be reconsidered. James Webb may be showing us that the universe is governed by physics we haven't yet discovered. And all of these theories are converging on one deeply unsettling possibility. The Big Bang might not have been the beginning after all.
For nearly a century, the Big Bang has served as our cosmic origin myth, the story of how everything began. But James Webb's discoveries suggest something profoundly different. They point to a universe that was already structured, already complex, at the moment of the Big Bang. Instead of emerging from perfect smoothness, our cosmos may have inherited organization from whatever existed before. Dr. Anna Salanti of New York University has developed models in which our Big Bang is simply the rebound from a previous universe's collapse, a cosmic bounce. In this scenario, the structures Webb observed could be fossils from a universe that came before ours. Other theories propose an eternal cycle of cosmic expansion and contraction, with each cycle preserving information and structure. Still others explore the idea of a multiverse, a vast network of interconnected universes exchanging matter and energy. In such a picture, the organization Webb detected may have been borrowed from neighboring universes. Some physicists go further, suggesting the Big Bang was not a creation event at all, but a phase transition, the universe shifting from one state to another, just as ice becomes water. In this view, the universe may never have begun, it simply changed. Dr. Abe Ashtakar's loop quantum cosmology replaces the Big Bang with a big bounce, a universe with no true beginning or end, only eternal cycles. These ideas redefine everything. If the Big Bang wasn't the beginning, then the question, what came before, becomes scientifically meaningful. The universe could be infinitely old. Our current expansion might just be one chapter in an endless cosmic story. This possibility challenges every assumption we hold about causation, existence, and the nature of reality. If the universe has always existed, then physical laws might be products of cosmic evolution. Life itself could have arisen in previous cosmic cycles. Webb may be showing us that we are not the dawn of cosmic history, but a continuation of something unimaginably ancient. We now stand on the edge of a scientific revolution. The evidence is reaching a breaking point. The standard model of cosmology requires increasingly strained modifications, more exotic dark energy, stranger dark matter, and inflationary models twisting themselves into knots to survive Webb's observations. Many physicists now ask whether it's time to abandon the Big Bang framework entirely, rather than continue patching it with unlikely fixes. Major scientific institutions are responding. The European Space Agency is funding missions specifically designed to test alternative cosmologies. The National Science Foundation is investing in non-standard models. The pace of discovery is accelerating, and every new Webb observation adds to a growing pile of contradictions. The probability that all of these anomalies are mere errors is nearing zero. The universe Webb reveals simply doesn't match the universe our theories describe. We may be living through a cosmological upheaval as profound as the moment Copernicus moved Earth out of the center of the cosmos. What seemed radical a few years ago now begins to look like the only explanation that fits. And if Webb forces us to rewrite the story of how the universe began, the consequences will reach far beyond science. Our cosmic narrative shapes our philosophy, our religions, our sense of meaning. Just as Copernicus reshaped humanity's place in the universe, and Darwin reshaped our understanding of life, Webb may reshape our understanding of existence itself. If the universe is eternal, if time and space behave differently than we assumed, if consciousness or information play roles we never imagined, then our deepest questions must be asked again. Why is there something rather than nothing? What came before the beginning? What is our place in an infinite, evolving cosmos?
Webb suggests that the universe may be older, stranger, and more wonderful than any theory we've ever imagined. If rocky planets and complex chemistry appeared billions of years earlier, life itself may have arisen long before our solar system existed.
We may not be the first observers, only the latest in a vast cosmic lineage. And if the universe preserves information through eternal cycles, then nothing, not even life nor consciousness, may be truly lost. Webb's discoveries remind us of something profound. The cosmos still holds mysteries far beyond our grasp. The greatest revelation may not be a specific new theory, but the realization that our universe is infinitely richer, deeper, and more mysterious than we ever believed. The inconsistencies revealed by James Webb aren't random quirks or isolated mistakes. They form a clear, repeating pattern, one that suggests our entire timeline of cosmic evolution may be fundamentally wrong. The statistical weight behind these discoveries is now so immense that the idea they're all just measurement errors or unlikely coincidences has become nearly impossible to defend. We're not witnessing accidents, we're seeing systematic contradictions that demand an explanation. This growing convergence of evidence is pushing physicists to abandon the idea of patching the existing model with small adjustments. Instead, they're being forced to consider radical new theories. As Dr. Sykestein Sabir Sarkar of Oxford University puts it, we're entering a paradigm crisis, a moment when accumulated anomalies simply can't be absorbed into the old framework anymore. History has seen this before. Major scientific revolutions, from the discovery of stellar parallax to galactic redshifts and the cosmic microwave background, overturned entire worldviews. Just as those findings cemented the Big Bang as our cosmic origin story, James Webb's discoveries may now be converging to dismantle it. Scientific institutions are beginning to recognize the severity of this crisis. Instead of offering temporary explanations or convenient excuses, major funding agencies are now investing heavily in alternative cosmological models, theories capable of explaining Webb's findings without violating the laws of physics. Behind closed doors in research centers around the world, physicists are racing to build entirely new models of cosmic evolution. These aren't minor tweaks, they're revolutionary blueprints that could replace the Big Bang theory altogether. Their urgency reflects the seriousness of the evidence piling up. Dr. Neil Turek at the Perimeter Institute is developing cyclic universe models, proposing that the cosmos expands and contracts endlessly, each cycle preserving structures and information from its predecessor. In this view, our universe may not have begun at all. It may just simply be the latest in an infinite succession. Meanwhile, Dr. Joe Mago at Imperial College London is exploring models where the speed of light was different in the early universe. If light moved faster in ancient cosmic times, distant regions could synchronize their evolution, explaining the large-scale organization Webb observed without requiring impossible timelines. If rocky planets and complex chemistry began billions of years earlier than believed, the universe may have been filled with life long before our solar system even formed. We may not be pioneers, but latecomers in an unimaginably long lineage of cosmic observers. Even our concepts of death and time could change. If the universe truly cycles eternally, preserving information between expansions and contractions, then perhaps nothing is ever fully lost. Not stars, not galaxies, not even consciousness. Webb's findings may be pointing toward a universe where existence itself is everlasting and indestructible. But shifting to such a cosmic story will be psychologically profound. Humanity has always relied on origin stories to understand its place in the cosmos. The Big Bang, despite being a scientific theory, also functioned as a modern creation myth. Yet the deepest implication of all may be this. Webb reminds us how much we still don't know. Just when we believed we understood the universe, it reveals layers of mystery we never imagined. The real discovery may not be a new theory, but humility, the realization that the cosmos is far more intricate, stranger, and more magnificent than we ever believed. The James Webb Space Telescope was built to confirm our story of cosmic origins. Instead, it may be revealing that the greatest journey in understanding lies ahead, hidden in the depths of existence itself. We aim to validate the Big Bang. Instead, Webb is shown as galaxies that shouldn't exist, stars forming impossibly fast, and structures far too organized for the universe's youth. The telescope designed to witness the birth of the cosmos may be writing the final chapter of the theory that once explained it. The evidence is overwhelming. Massive galaxies appearing too early, heavy elements forged too quickly, rotation speeds that defy physics, collision signatures older than possible, star formation rates beyond theoretical limits, and planetary systems built before their ingredients even existed. Individually, each anomaly might be dismissed. Together, they form a picture of a universe that refuses to obey our rules. This isn't a scientific inconvenience, it's a revolution. Webb's discoveries force us to question not just when the universe began, but whether it had a beginning at all. We may be living through the end of the Big Bang era and the birth of an entirely new cosmic story. If time and space behave differently than we assumed, if the universe has existed forever in some form, if cosmic evolution follows laws we have yet to discover, then every certainty we have about existence must be rethought. The questions that guided humanity for millennia must be rewritten, and yet the greatest revelation may be that the mystery is larger than we ever imagined. Webb shows us that the universe is stranger, richer, and more awe-inspiring than any theory. The greatest revolutions from Copernicus to Darwin to Einstein began the same way, with observations that didn't fit the rules. We may now be standing at the beginning of a new revolution, one that reshapes not just cosmology, but the very nature of reality. We stand at the threshold of a new cosmic narrative, where the universe may be eternal, infinite, and profoundly mysterious. The telescope built to confirm our origins may instead be opening the first page of a colossal new chapter. The greatest discoveries are not behind us, they're ahead, shining from ancient galaxies that defy our understanding, spinning stars that break our physics, and a cosmic architecture that seems to know more than we do. The story of the universe isn't ending, it's only just beginning.